Welcome to today's session of analog microelectronic circuits class. In the last class, we were discussing about open loop configurations of op amp. There we discussed about basic comparator, inverting and non-inverting comparator, and we also, after looking at a zero crossing detector, we also identified that there are some limitations, so there are some issues with open loop op amp circuits. The problem is uh, um, many a time the noise present at the input terminals is detected as input, the actual input, and especially in the case of slow varying signals, the noise at one of the input terminals will cause random fluctuations at the output. So what is happening is whenever such noise is present, that is creating confusion in the op amp input side whether should respond to that specific input or not. So such issues are solved, or such issues can be solved if we establish a positive feedback in the circuit, and that circuit is called a Schmitt trigger. That is what we discussed last class. So today we will continue that. Today we will see how the Schmitt trigger can be a useful circuit, especially when we have this kind of issue with an open loop circuit, right? So Schmitt trigger. So Schmitt trigger is a circuit which you have already experienced in lab, right? So one thing, if I ask about Schmitt trigger, like what is that one thing you observed in the case of a Schmitt trigger? Can I get some response in the chat box? What this Schmitt trigger generally does? Yeah, there will be a change in output waveform. Uh, Generally, we provide a sine wave input, right? Control VRF by using two resistors. Yes, all those things are right. So generally, we provide a sine waveform, and for a sine, if the input is sine waveform, Schmitt trigger generally act as a squaring circuit. So for that reason, we also call Schmitt trigger as a squaring circuit. So when you give an input as sine wave, you will get a square, since it is converting, since after setting the threshold, after setting the upper threshold point and lower threshold point, there are two threshold points which is set by the feedback resistors. With the help of that, your output will be switched between plus Vz and minus Vz. So basically it converts a sine wave to a square wave, and for that reason we call it as a squaring circuit. Right. So there are various forms by which we can realize Schmitt trigger, and one such form is, so let us look at a so the basic circuit of Schmitt trigger comes from an inverting comparator. So we discussed about an inverting comparator, but in the case of inverting comparator there is no feedback element. But now if you introduce a feedback element, if we introduce a feedback portion in an inverting comparator, we can call it as a Schmitt trigger. So Schmitt trigger is basically an inverting comparator with a positive feedback. Yeah, and this circuit, so whenever we go for an inverting comparator, say minus plus, so input will be given to the minus terminal because we call it as an inverting comparator. So here we provide input signal, say V in, and since we want to establish a positive feedback, what we do is a portion of output is fed back to input. So this is V out, and this resistance we call it as, say, R1 or R2. Alright, so this is a circuit. So this is an inverting comparator with a positive feedback, and the speciality of the circuit is this circuit generally converts an irregular shape. If it is an irregular shape waveform also, it will be converted. So generally in lab we will test using a sine wave, but in some certain applications we will have a slowly varying signal where it will not be having a proper sine wave shape. It could be some information. So even an irregular shaped waveform will be converted into a square, or sometimes it will be converted into a pulse, right? So generally we call this as a squaring circuit. Now how this works is, so we know that the input is given to the minus input terminal, and whenever there is an input signal, so in the previous case we had a reference signal, but now input signal is the only thing which can trigger the circuit. Alright, and what we know about this is, um, when there is a change in the input signal, that will definitely create create an output, right? Because since it is an inverting comparator, whenever input signal changes, whenever input signal goes positive, we can expect that the output will go minus Vsat, because it's basically an inverting comparator, right? So let us look at the operation of the circuit by looking at the waveforms. Alright, so I am considering an input waveform. Alright. So now, whenever we talk about the input variation, every time that variation will be compared with reference voltage which is forming here. This is the reference voltage. So, can you tell me what will be this reference voltage? The voltage at the positive input terminal. How can I write the reference voltage at the output terminal? Sorry, not the output terminal, at the positive, the non-inverting input terminal. This voltage will be always equal to V out into R2 divided by R1 plus R2. V out into R2 by R1 plus R2 is the voltage which is appearing at the non-inverting input terminal. So every time the comparison is between the input voltage and the voltage which is coming over here. Now what is the difference here? We know that V out can be either plus Vsat or minus Vsat. Because of positive feedback, V out can be either plus Vsat or minus Vsat. Now, if your V out is plus Vsat, we call this threshold point as, if your V out is plus Vsat, okay, let me write it here. Yeah, so if V out is plus Vsat, we call this as, so what will be the reference voltage? Vsat into R2 by R1 plus R2. We call this as upper threshold point, for the reason that this is actually giving you a threshold voltage which is higher. Now when your V out is minus Vsat, the output will be minus Vsat into R2 by R1 plus R2. That will give you a lower threshold point or LTP, right? So if output is at plus Vsat, we call the threshold point as upper threshold point, and if the output is at minus Vsat, we call it as lower threshold point. So what happens here is the input voltage, the input voltage which is connected at the inverting input will trigger, or it will change the state of the output, right? So how it will change the state of the output? Whenever the input voltage exceeds certain voltage level. So the voltage levels here are upper threshold voltage and lower threshold voltage. So whenever this V in exceeds this UTP or LTP, the output will switch, right? So let us look at the waveform to understand this circuit better. Yeah. So look at this. In this case, based on the output signal, I can mark, based on the output, let me mark this as the upper threshold point and this as the lower threshold point, right? Now how the circuit works, if you look at this, maybe I'll assume that the input signal is starting from 0. Now for that, yeah, so from when the input signal varies from 0 to the point which is equal to upper threshold point, can you tell me what will be the output? So the moment, so the moment we say that upper threshold, so here if I consider this point, upper threshold point is there here. I am assuming, so when I say I am assuming upper threshold point here, the meaning is what I have at the output is plus Vsat, right? So at plus Vsat, when output is at plus, I am assuming that there are only two states. So if I assume that initially if your output is at plus Vsat, then the threshold point is upper threshold point, and then if the input signal is smaller, if the input signal is less than upper threshold point, then we can say that till this point, since my threshold point is there, till that point I can consider my output as plus Vsat. Alright, so yeah. So till this point I can consider the output is at plus Vsat. Now what happens? The moment input signal crosses upper threshold point, which terminal is having higher voltage? Minus terminal is having higher voltage. So what will happen? The output will go to minus Vsat. So the moment the input signal crosses the upper threshold point, the output will switch and it will go to minus Vsat. So this is minus Vsat. So soon after output goes to minus Vsat, what happens? Now the threshold point becomes lower threshold point. Because since the output is minus Vsat, the threshold point becomes lower threshold point. Now the reference point will become this, right? So the entire duration from here till this point, output will remain in minus Vsat, because since here the next threshold point has come to lower threshold point. Now if the output wants to go to plus Vsat, then your input signal should go below the LTP value. So till this point output will remain at minus Vsat, and at the moment when your input signal crosses this lower threshold point, look at this point. At this point your positive input terminal is having soon after the input signal crosses this point, what happens? Your negative input terminal is having a lower voltage compared to the positive reference voltage, and as a result of that, what will happen at this point? The signal again switches. The moment output goes to plus Vsat, now the reference point will become this, right? So once the reference point become plus Vsat, till then it will remain in plus Vsat, and again this cycle will continue, right? So this is how a basic Schmitt trigger works. So it basically works with the help of two threshold points. One is upper threshold point and another one is lower threshold point, right? So what happens here, whether the input signal is a slowly varying waveform or a fast changing waveform, depending on the output signal, the threshold point is set immediately. The threshold point here becomes a UTP or LTP depending on the output signal. So thereby the false transitions can be avoided here, right? Because every time the threshold point is changing with respect to output signal, it becomes either plus Vsat into R2 by R1 plus R2 or minus Vsat into R2 by R1 plus R2. As a result of that, the transitions will be based on the threshold point, and threshold point is every time changing with respect to the output signal. So since the threshold point, the UTP and the LTP are made larger, so the basic reason here is the threshold points are made larger than the input noise voltages. Input noise voltages are very small, and the reference is not at all zero. The reference is switched to upper threshold and lower threshold point, which is larger than the input noise signal, and for that reason that is possible with the help of this positive feedback. So thereby this positive feedback is actually eliminating the false output transitions, right? Now yeah, so this is how a basic Schmitt trigger works. So as I have written here, this is the these are the design equations or the expressions. So let us quickly design Schmitt trigger based on what we understood now. Let us look at this. If you have questions, please put it in the chat box. So design a Schmitt trigger with upper threshold point as 1 volt and lower threshold point as minus 1 volt, given that the supply voltage VCC equals 12. So when it is given that VCC is 12, it is assumed that the other negative terminal voltage is minus 12. Alright. So so how will you design? There is a UTP voltage, there is an LTP voltage. So what we can do is we can go ahead with the circuit what we have discussed so far. No, that will work, because this is input V in, then this is a positive feedback. So This is how we configure. This is V out, this is R1 and this is R2. Now design in the sense we have to come up with the values for R1 and R2 so that the threshold points will be 1 and minus 1, right? So for that we can write upper threshold point as plus Vsat into R2 by R1 plus R2. So given that VCC is 12, so you can consider plus Vsat as that. So 1 is equal to 12 into R2 by R1 plus R2. Or you will get that R2 by R1 plus R2 is equal to 1 by 12, right? So one way to choose the resistor values, assume R2 as 1 kilo ohm and R1 as 11 kilo ohms. This is the simple way how we can get the values, right? Now one more important thing with respect to Schmitt trigger is, so Schmitt trigger can be considered as a regenerative comparator. Now look at this. If I plot input voltage versus output voltage of a Schmitt trigger, so this basically, so what I'm trying to draw here is a transfer carrier of Schmitt trigger. So now Schmitt trigger basically works on two threshold voltages, right? One is here upper threshold voltage or upper threshold point, the other one is here lower threshold point. So this is based on the general discussion that your UTP and LTP are symmetric and equal. So there are various headings we can consider, we can study Schmitt trigger. One is symmetric symmetric in the sense it is like plus V plus if the UTP is plus 1, what I'm telling is the LTP is minus 1. So let me write it like this instead of writing it as symmetric. Threshold points are equal and opposite, equal and with opposite polarity. This is one case. So for that, if we draw the transfer carrier, what we know about Schmitt trigger is whenever the input voltage crosses UTP, what happens? Look at this. Whenever the input voltage crosses UTP, output will go to minus Vsat. So if we draw the transfer carrier of a Schmitt trigger, let me mark this point as plus Vsat and mark this point as minus Vsat. And the moment input crosses upper threshold point, this will switch to, so till this point it will be plus Vsat, then this will switch to minus Vsat. Alright, it will switch to minus Vsat. Now after switching to minus Vsat, whatever we do with the input signal, if we still increase input signal, what will happen? It will continue in that minus Vsat only. Right, it will continue in minus Vsat whenever we increase input voltage after UTP, because soon when the output switches to minus Vsat, the threshold point also switches to LTP. So whatever happens to the input signal beyond UTP, how much ever the input goes high, the output will continue to remain in minus Vsat, right? Now what will happen, as the input voltage reduces, it will also reduce, and when the input voltage reduces UTP, nothing will happen, it will continue in minus Vsat. Now if the input voltage falls below LTP, what will happen? Then output will go to plus Vsat. So go to plus Vsat. So it is like this. Now once the output switches, even if your input signal goes below, so once it goes to plus Vsat. Now after switching to plus Vsat, even if the input signal goes lesser than that, nothing will happen, because soon after switching to plus Vsat, the reference voltage becomes UTP. So even if you reduce the voltage further, nothing will happen. It will be continuing in plus Vsat and it will go back, and then the next switching will happen only when the input signal crosses UTP, right? So this is how we draw the transfer carrier of a Schmitt trigger. This is how we draw the transfer carrier of a Schmitt trigger. And this portion where we have this shaded portion, we call it as hysteresis of Schmitt trigger. Alright, so the meaning of hysteresis is Within this, so the circuit will respond only after UTP. So when the input signal crosses UTP, it will respond. It will change from plus V side to minus V side. Then again, the input signal crosses LTP, it will change. So inside this, there is no detection, right? Inside this, the state will not change. The state of the Schmitt trigger will not change within this box, and this region is known as hysteresis, where there is no change, or this is called a dead band condition. Dead band condition. So dead band condition or hysteresis is common in the case of comparators, and when you say comparators, the comparators will respond only. Comparators will respond only when the input signal crosses a particular point. So where the comparator is not responding, or where the comparator continues to remain in that state, that condition is called as dead band condition or hysteresis of a Schmitt trigger. So the comparator with positive feedback is generally to exhibit a hysteresis or called a dead band condition, right? Alright, so so how to write the hysteresis voltage? Hysteresis voltage, if I am writing it as V hysteresis, it is generally written as upper threshold point minus lower threshold point. So in this case, that is equal to R2 by R1 plus R2 into plus Vsat minus Vsat. This is how we write the hysteresis voltage of a Schmitt trigger. Alright, so this is the general, or this is how in general a Schmitt trigger works, and for the said reason, like since the threshold points are much higher, the circuit will not be responding to the noise voltage signals also, right? Now this is the first case where I told that the input, the threshold points are equal and with opposite polarity. There will be different requirements whenever we go for comparators. So another type is, or another type how we can decide is threshold points are unequal. Need not be always threshold points need not be the same, right? There may be situations where we need switching at different voltage. So whenever threshold points are unequal, again with opposite polarity, then also we might need this kind of circuit. So we will look at the design of one such circuit now. Yeah. So the question is, design a Schmitt trigger if UTP equals 2.4 and LTP equals minus 4.8 volt. Again, assume that VCC is 12 volt and VEE is minus 12 volt. So can you think on this question where I need a positive UTP, like the UTP is 2.4 and LTP is minus 4.8, two different voltages, right? So this requirement or this condition says that the circuit what we have considered in the given form is nothing but this is the given form. In this form we cannot use it because we have this resistor R1 and this resistor as R2. This is V in, and in this form with only R1 and R2, is it possible to design with only R1 and R2, is it possible to design for two different threshold points, is what the question is. So please think on this and just give your comments on the chat box. If there is a question, when V in crosses, V in is greater than LTP, it should be only minus Vsat. What is that? When your input voltage is greater than LTP. So if you are let us look at this. No? Input voltage is greater than LTP is this condition. Yeah, it is minus Vsat only, correct only. In hysteresis curve, alright. When your input voltage is greater than, what do you mean by greater than? Greater than means here, right? This side. then your output is at, one second, what we have done here. Yeah, look at this. Here your input voltage is greater, right? And then your output is minus Vsat. The moment your input becomes smaller than LTP, output becomes plus Vsat. The moment input becomes smaller than LTP, output becomes, yeah. So yeah, when you look at this hysteresis curve, no, this is how you have to look at this. See, you have threshold point and you have input voltage here, right? So now what we have here is an inverting comparator, that also you have to keep in mind, right? So we can also we can also design in a non-inverting fashion, that also is possible. We will see how we can do that. The non-inverting type of comparator also we will see how we can do. Now in the case of a inverting comparator, see, look at this, how this works. When your input voltage crosses UTP, crosses UTP, the output is actually switching to minus Vsat. Input voltage crosses UTP, output is switching to minus Vsat, right? And after that, when the output switches to minus Vsat, the threshold becomes LTP. Now what happens, even if your input voltage is increasing beyond UTP, the output will continue to remain in that state. Nothing will happen there. Now when your input signal becomes smaller, and when your input voltage becomes smaller than LTP, then what happens? So your input voltage is becoming smaller than LTP, then your output is actually switching to plus Vsat. See, here the switching is happening to plus Vsat. That is what I explained. Yeah. Now, so what to do for this condition? This is the requirement. Now we have to design a Schmitt trigger where you have alright, you have a UTP 2.4 and LTP minus 4.8. So how will you design this? See, one thing is sure, with a single path like this, it is difficult to have two threshold points. The reason is because see here, output can be only two conditions. Output can be either plus Vsat or minus Vsat. So if the output is at plus Vsat, the threshold point becomes UTP. Output becomes minus Vsat. Threshold point becomes LTP. Right. Now we have two equations. Like what we have designed now, we have two equations, but both equations are, since both equations are same only with the polarity difference, we can also the possibility is to have equal threshold voltage but with opposite polarity. There is no other possibility with this simple circuit. So what can be done in this case? So what is the requirement? When you're see, how can I write UTP? UTP is equal to plus Vsat, which is 12 into R2 by R1 plus R2, and LTP is equal to minus 12 into R2 by R1 plus R2. Yeah, we can do with the help of a reference voltage, that is one thing. But when you add a reference voltage, yeah, that is possible. That is another possible way. In a simple way, by applying a small modification, yeah, we can actually do this with the help of diode. So basically the need here is, for a UTP and LTP, since I have different voltages, I need different resistors for that, right? Since these two are different, I need different resistors. Which resistor I'll ask for, which I'll make for different? I want this resistor to be different. Why? Because when the output is at plus Vsat, I want to set the threshold point through this. When your output is at minus Vsat, I want to set the threshold point through a different path. So how will I do? What I can do here is, I'll have two resistors here. Now when the output is at plus Vsat, I want the upper resistor to work. Let me call it as R1 dash. Now to make this resistor to work, I can actually add a diode in this form, and this path will be enabled only when your output is at plus Vsat. This diode will turn on. So at that moment, the other path should be disabled. So I should add a diode in this form, and I'll call this as R1 double dash. Alright, so when your output is at plus Vsat, what I can write is R2 divided by R1 dash plus R2, and when your output is at minus Vsat, I can write it as R1 double dash plus R2. Right, so with the help of these diodes, with the help of diodes connected in this fashion, which can route the signal, route the output point through two different paths, we can actually set two different threshold points. right? So can you quickly design and let me know what are the values for R1, R1 double dash and R1 dash with this? I'll say I'll take R2 as 1 kilo so that you can fix the other one. Yeah, R1 dash is equal to 4 kilo ohm. Yeah, and similarly R1 double dash is equal to, you can quickly solve this using these two expressions. Yeah, so if you solve, you will get R1 double dash as yes 1.5 kilo ohms. All right. So this is how you design Schmitt trigger with unequal threshold points are unequal with opposite polarity. So there is one more category. What we can do is uh, threshold points unequal with same polarity. It could be either both positive or both negative. So that, let us see that with the help of another design question. So design a Schmitt trigger with UTP equals 2 volt, LTP equals 1 volt. Given that VCC equals 15 volt. So when you have both the threshold points as positive or with same polarity, then definitely UTP and LTP will be unequal only, right? So in that case, none of the previous circuits will work, because the first circuit will work only for equal and opposite threshold points. The second will work again with different UTP and LTP values but with opposite polarity. Now for this one, generally what we do is we can there is one method whereby we can add a reference voltage instead of yeah, from the basic circuit. The difference is this. So this is R1 and this is R2. So instead of keeping this point as directly ground, we can add a reference voltage here, and with the help of this reference voltage we can actually switch, or we can switch the entire threshold points to positive. So this is V in, this is V out. So you can write equations and find the relation between write equations to get the upper threshold and lower threshold points. Here directly I'll give you those values. So upper threshold points you can get as this Vref, which is added to the difference voltage VCC minus Vref into R2 by R1 plus R2. Similarly, LTP can be obtained as Vref plus minus VCC minus Vref into R2 by R1 plus R2, where UTP, Vref and VCC values are given. Now what you can generally, how you can solve this is take this factor R2 by R1 plus R2. Let us assume that this factor is some x, right? So what we can do is this R2 by R1 plus R2 depending on the conditions given. So you can substitute this as x, put all the values. So UTP values, UTP is given, LTP is given, reference voltage is given, VCC is given. So with two equations you can actually find what is unknown x, and after getting this x value, depending on the x value, say for example if you are getting x value as some say some 2 by 12 2 by some value, so for example I'll just take it as if I'm getting this ratio as 1 by 30. So depending on this, I'll choose a value for R1 and a value for R2. That will definitely give you the required threshold points, because we have designed with this upper threshold and lower threshold points, right? This is another way. So this is possible even in the other case. So by specifically choosing a reference voltage, we can switch the threshold points both towards positive or both towards negative, depending on what reference voltage we take, right? So this is the third category what I was mentioning, where you will have different threshold points, but both with same polarity, right? This is another type. So these are the various types of Schmitt trigger designs, and probably we'll wind up today's class here. If you have questions from this, please do ask.